Hello students, in this video we will discuss the energy and the conservation force. Okay, and we have already considered a system which is consist of a large number of small particles. Okay, but these particles still obey the classical mechanics rather than the quantum mechanics. Okay, then the kinetic energy for this particle of the system is T is equal to we can say for one particle, okay, then this is 1 over half m1, and we can write this is not v but like this m1, okay, or dot 1 square, and then 1 over 2 m2 and r dot square 2 and so on. Okay, there is number of particle is n particles. Okay, and then we can write this in the form of summations is 1 half is mi and r dot square I. Okay, this is the kinetic energy of this system, which is consists of the large number of small particles. Okay, is in the case of the angular momentum, then we can also hear the T is can be separated into the center of mass in the relative terms. Okay, and then we consider we already know the Ri is equal to the R, this is relative, and this one is the about the center of mass. Okay, then we can write like this, this is the derivative. Okay, then we put here this value. Okay, then the T is equal to summation 1 half mi, and here we put the value of this. Okay, and then this is the r dot plus I whole square. Okay, and then summations as 1 half mi, and we're using the squaring formula, and then the square of first. Okay, and then plus summations 1 half mi, and then the square of this is r dot plus, and this is a square. Okay, and I, and then plus 2 times of this and this, and then this is 2. First we write the summations. Okay, then summation I and 1 half and mi, and then we can write its 2 times is r dot and r dot plus I. Okay, then this 2 is cancelled to this 2, then we can write these equations. This is only is the summation is applied on the mi. Okay, and then this is the total mass. Let us look here, the mi, the summation of the mi, this is the total mass of the system, this systems. Okay, this is the capital M of 1 half here, and this is the r dot square, and then plus. Okay, and then the summations of I and 1 half of mi and r dot plus and square ri, and then plus the summation of I mi and and then the r dot plus r dot plus I. Okay, then we know the capital M R plus, okay, this is plus about the center of mass, and the summations of the Mi and R plus I, okay, this is equal to 0. Now this term is goes to 0. Okay, then we can write this is 1/2 capital M, this is R plus, and here this is R dot only, and this square, and then this is the summations of I and 1/2 Mi R dot plus square I. Okay, and where this kinetic energy is the kinetic energy relative to the center of mass. Okay, now this is the T plus, which is the relative to the center of mass, is summation 1/2 Mi and R dot plus square I. Okay, this is the kinetic energy relative to the center of mass. Okay, and this relations is for the two particle systems. Okay, then the momentum and the angular momentum and the kinetic energy and the any parameters, we have already discussed the momentum and the angular momentum, the X conversations, and all these things, and here we discuss kinetic energy conversations. And then any parameter are obtained from the those and the center of mass frame. This is the center of mass frame. Okay, and adding the contribution of the particle of the mass capital M at center of mass. This is the center of mass positions. Okay, this is the kinetic energy, and there is also for the angular momentum and as well as for momentums. Okay, we can obtain like these equations. Okay, at any frame we obtain from those and the center of mass. This is the center of mass kinetic energy. Okay, and adding the contributions of the particle of mass capital M and located at the center of mass R. Okay, then we take the derivative of the kinetic energy. We know the kinetic energy is equal to summation 1/2 and MIR dot square. Okay, I. This is the kinetic energy. Now we take the derivatives. Then d divided by dt, and then this is the summation and 1/2 mi, and we take the derivative of this is r dot square I. Then summation 1/2 mi, and the 2 is come here, and 1 is minus to its power, and this is the r dot I, and then we take the derivative of the r dot I, then this is the 2 time derivative. This is the first time, and then the next one is ri. Okay, then this 2 is cancelled to this 2. Okay, and then we can write this change is like a dot. Okay, and this is the summations of the r dot I, and then dot mir double dot I. Okay, now the x value is equal to the mir double dot I value is equal to the fij and plus the summations of the I r dot I and f. Okay, and this video we have already discussed in the previous videos. Okay, and then we put here the summation mi and r dot I, and this is the dot, and we put the value of this as the fij. This one is the internal force, okay, between the two particles, and then this is the external ones. Okay, is the this is here, this is not, this video is like this. Okay, this is video is m or dot I is equal to the fij, and then the summations of the fi only, this one. Okay, not test. And then we multiply this to this value. Okay, we multiply this into this r dot into the fij, and then multiply to this ones. Okay, and then let's the contribution from the internal port. This is the internal ports. Okay, is like a two particle system is 1 and 2. And then this is we have already discussed, or the according to the Newton third law, this is equal to this one, and this is also equal to the same force F's. Okay, between the particle 1 and 2. Then we can write these equations like, and here only this term. Okay, we simplify this term only, and then this is the r dot 1 for the particle 1s, and the corresponding force is this, and then r dot 2 and the corresponding force is 2 1s. Then we put the value of this here, and this is the r dot 1s, and here the x value is equal to f. Okay, and then we can write direct minus, here is minus, then this is the minus f. Okay, then the minus is here, then this is r dot 2 and dot f's. Okay, then we take common f, this is r dot 1 minus r dot 2 into f. Okay, and this is equal to is the r dot. Okay, this is equal to the r dot f. The r dot 1 minus r dot 2 is equal to the r dots. Okay, this is, here is our dots. Okay, the rate at which the pulse does works. Okay, the change in the kinetic energy is cannot written only in the external pulse, and this is not surprising. Okay, this change and the kinetic energy we cannot write only in the external force only. Okay, there is also the internal energy, the internal potential is also changed, so we can write also the internal force. Okay, okay, and there is some special case in which the pulse does no work. Okay, and may be omitted from the energy change equations. For example, if the r dot is equal to 0, the change in the position is equal to 0, or we can say the if this is a pulse is always perpendicular to the r dot. Okay, is perpendicular to the r dot, this is a special case. In the case of the rigid bodies, okay, where the positions of the body is fixed, when we apply a force on the rigid bodies, okay, let us look here. This is the two particle. This is particle 1 and this is 2. If we apply a force on this rigid body, then the distance between these two particles does not change, okay. Now then this is a rigid body, and this is the property of the rigid bodies, okay. Now then the distance between the all particle is the same, where if there is a number of particles, then the distance between the all particle are fixed. Then we can say the r is constant, okay. The r is constant, okay. The distance between the two particles or the number of particles is constant, okay. Or we can also find like this. This is the, we can write this is like this, is d divided by dt is equal to 0. Then we can write dr is equal to 0. Then we integrate both sides. Then this is equal to r. The d is cancelled to this. This is 0, integration is constant. And this is constant, okay. Okay. Now then the r dot and the x dot with the r is equal to 0, okay. If the force is central, okay, if the force is central, now then it is the same direction as the r. Now then the force is parallel to r, and here is perpendicular, and here when the force is central, in this case the force is parallel to this r, okay. And r is perpendicular to the r dot, but this force is perpendicular to the r dot. This is r dot, this is not r, okay, and this is perpendicular to always this ones, okay. And this the central force between the particles, whose distance is apart is fixed, does no work. Now, so this is like this situations here also. This is perpendicular to this, okay. Then if this is a central force, then this is perpendicular to this, and here there is no work, okay. Thank you.